this idea of why we need to or rather how we pass in the information of the address at which a particular device is connected requires some kind of a solution, right. Now as we have seen over here, one way by which we can solve it is to basically say, when I load the module, I will pass the physical base address to it, right. Now you need to remember a couple of things over here. Number one, I am the person building the hardware, or in this case I am the one actually constructing the Renode REPL script, right. And that means that as a hardware designer, I must know at which physical address a particular device is connected, right. If I don't know that, there's pretty much no way that I can write a driver, right. I cannot expect the kernel to randomly go around probing all the 2 power 32 addresses that are present in the system, right, in order to find out where something might be connected. Not just that I cannot expect it to do that, if a system ever tries to do that, it is going to be very dangerous, because the only way I can sort of detect a particular thing is by trying to read from an address. And as you have seen, depending on how hardware is constructed, even just reading from an address might be enough to actually modify something inside the system, right. There are, for example, we have already seen how we can write a register or a flag which clears on read, right. Just the act of reading from the register is enough to change the flag setting to 0. How does that work? Basically it sort of detects that this address has now come onto the bus and it makes some internal changes inside the hardware. So I clearly cannot go around randomly sort of searching all the different addresses that are present. As a hardware designer, I need to know which address I have connected the system at, right. My module, whatever it might be my smart timer, it might be a UART, it may be a ADC driver for some custom software defined radio project, right. For each and every one of those, I need to physically know where exactly I have connected the device. Now that is literally a part of the electrical connections inside the AXI bus, right. But once I have made that decision, I also need to pass that information through to my hardware. And as we saw, of course, I can pass in this parameter physical base, and that's good enough, right. The hardware now knows that there are these devices that have been created. I can now use those in order to access the different parameters that are present inside the system, and so on and so forth, right. Now the problem with this approach is it doesn't scale. And what do I mean by doesn't scale? The thing that you need to understand is we are never building just one particular computer, right. What we talk about as a computer could be many different things. The computer where I am giving this presentation right now happens to be a desktop PC, right, from a particular manufacturer with a certain amount of disk space, memory, a certain type of processor, a certain type of RAM attached to it, a certain set of Ethernet cards and various other things connected to it, right. Now very likely somebody else's laptop might consist of very similar things, in the sense that it might still be an Intel processor, but it's a different processor than the one that I have got, right. It might have memory, but not the exact same type of memory chips that I am using. It might be using a hard disk, but not the exact same brand or the size of hard disk that I am using. So now this starts to complicate matters, right. I cannot, or rather it's not easy to create a custom kernel for each and every new computer that you build. Now before you dismiss that out of hand, please keep in mind that the original computers, that's pretty much how things had to be done, right. I mean, you had to pretty much, if I created a new system, I literally had to hard code all of this data into the kernel, compile it and then boot onto it, right. But we don't want to keep doing that. We want to sort of scale. We want to make it easier for us to write one kernel, right, one piece of software, one ELF file that I can load into the memory of the system. And that ELF file should have some flexible way by which it can find out everything else about the system, okay. So if I need to sort of go in there and physically write a script that says, okay, load this particular driver at this address, load another driver at another address, that is complicated in itself, right. I need to make sure my drivers are all compiled properly, which is fine. I need to do that anyway. But then for each and every different parameter that I create, I need to now go in there and say, okay, this is the exact set of devices that are present over here, and I need to create a device tree, or I need to create some kind of script that will load in the different modules into their appropriate locations. Now the device tree tries to solve that problem in a slightly different way. You still need to specify all of this information, but what they say is let's try and do it at one shot, right? Rather than every time I change the kernel, every time I recompile something, having to go in there and create a new set of scripts that say, okay, load this at this particular location and so on. I'll create a description of my platform, conceptually very similar to what Renode is doing with the REPL file, right? And use that. Let me just pass that information into the Linux kernel, and the kernel can then sort of read through that and figure out how different things are connected to each other. Okay. So the device tree solves exactly that problem, right? What it says is we are not writing code in order to load in our drivers. We'll provide some kind of data, right? We describe the hardware once, and this has to be done for every single new hardware that you create, right? But once we have done that, we can then reuse the drivers. Now, another example which might be a little easier to understand, if you have worked with this system called the Raspberry Pi, right, is actually the Raspberry Pi and the corresponding ecosystem around it, right. Those of you who have worked with Raspberry Pi systems might have heard that there was a Raspberry Pi A, then there was a Raspberry Pi B, then a B plus, then a Raspberry Pi C, and I believe there are other variants of it now, right. So the question is, do people keep going around recompiling the kernel each and every time they have a different model? Well, sometimes they might, because there might be new devices that actually need to be compiled in, or it might just be that the kernel itself has improved in certain ways and they want to take advantage of that, and therefore they recompile it. But the interesting thing is, rather than sort of going around specifying exactly what particular module is placed where, they use the data, the device tree, in order to specify how the different blocks are connected inside the Raspberry Pi. And this is sort of a text-based description of the Pi platform, right, which is actually, you can read it, you can understand it, and it actually gives you a lot of insight into how the entire system is connected. Okay. Now, what happens in practice is that the people who created the Raspberry Pi need to create something called a bootloader. Now, what is the bootloader? We already, in the case of the Renode emulations, we have not really had a bootloader. We pretty much said that there is something that can load an ELF file into a particular location in memory, and once I have done that, the system just takes off from there and runs. Now the interesting thing is, if you think about how a Raspberry Pi boots, the operating system for the Raspberry Pi is not actually flashed into a very specific location in memory. It comes from the SD card, right? Now how do I read from an SD card? That itself is a piece of hardware which requires its own driver, right? So it sort of looks like a circular argument, and that's literally what the idea of bootstrapping or booting is, right? The way that it is done in practice is, there is sort of what's called a first stage bootloader, whose job is to have just enough device drivers to be able to read from the SD card, take some data, put it into an appropriate location in memory, the equivalent of the loadelf command that we gave in Renode, and then jump to that particular location and start executing. The good thing is, because we now have the small piece of software which acts as a so-called bootloader, it can also read in a device tree and put it in a specific location in the memory once again, and the kernel can then pick it up from there, right. Now there are a few terms which we will look at in more detail as we get into the device tree. For example, there is something about compatibility of drivers, the specifications of where the registers, the addresses are, what kind of interrupts are being used, all of that is passed in as part of the device tree, right. Which means that we can pretty much write and compile one kernel and use it on many boards, right. So all the different Raspberry Pi boards, or all the different Xilinx zinc based boards, right. For example, the Z board, the Pink Z1, the Pink Z2 are sufficiently similar that they could probably share a kernel and just have slightly different device trees that enable them to sort of load in the different drivers that they need. Okay. So before we get into the details of what a device tree specification looks like, this is roughly what code would have looked like before the device tree idea was implemented, right? There would be some C code somewhere in your kernel itself where you would have some kind of a new struct, a type def, right, where we specify the resources used by a UART, right. And you can see the kind of resources that I am specifying. For example, it says that there is something called start and it gives a hexadecimal number out here. It gives end and another hexadecimal number. It also uses some kind of flags which basically seems to indicate that this requires an access to IO and is also memory mapped, right. It also has another set of another sort of block of data out here which says, for example, start is 5, end is 5, and that this is the IRQ, right. So if we think about it, right, the kind of information that this is providing is, this first entry over here is telling you what is the memory map range, right, the starting address and ending address that you require in order to map your particular device into memory. The second one is saying I have an interrupt associated with my UART. For example, it might be that every time I have received a new byte on the UART, I generate an interrupt. Now, the way that interrupts work in practice is that I have something called an interrupt controller. I connect many different peripherals onto that interrupt controller, and that interrupt controller in turn finally goes and wakes up the CPU anytime that there is something new to be done, right. And which means that that interrupt controller also needs to be able to tell the CPU which device actually woke it up, right, or interrupted it. And that is done by specifying an interrupt number, right. And essentially what this is showing is that this is the kind of information that I need to pass in to the kernel so that the kernel then knows how to talk to a particular device, right. And in the absence of a device tree, I am literally writing code for this, right. I need to sort of specify the addresses and the type of resource, the number, as well as the fact that it is a IRQ number. All of that is sort of passed in as some kind of an array of different structs that we have over here, right. And finally, what I would do is I would basically define something called a UART device, which is of the type platform device. I would be able to, once again, because these are structs, the syntax that we are seeing over here is essentially the sort of named mapping of data to struct, data to the elements of the struct, right. So in other words, I have something which is name, which is a char star, a string. I have an ID which is probably an integer, num resources which is some kind of a pointer, right, an array, or rather num resources is probably an integer, and resources itself is some kind of a pointer, right, so it can point to this particular array. In other words, what we are doing is that we create this particular struct once again in our code, right. So you can see hopefully where I am going with this. The point I am trying to make is that if I wanted to create, let's say, a new UART, or to take our example, to attach a timer into my system, I would need to write all of this code and say, okay, this is the starting address, this is the interrupt. In our case, we don't yet have an interrupt. If we add it, we could probably put that in later. I would need to create a particular platform device corresponding to this. I would need to sort of give it a name, and then finally I would need to attach it by probably calling some kind of a function, right. Now the device tree approach takes whatever we had out here and tries to sort of simplify that and say, I am just providing text, this is not code, this is not C code that you are seeing over here. I have a name, I am telling you what kind of device it is, I am also telling you the address at which it is present, but all of that is just sort of a name that is given out here, right. What is important is, for example, this word out here which says compatible, which says that it is compatible with ARM and the PL011 UART, okay, which basically actually tells you that potentially you could have multiple different kinds of drivers that are available, and the system can sort of pick which driver is going to be used in order to actually activate this particular device, right. This compatible is just given as a string, right. So this, what I am showing over here is an example of what a device tree entry would look like, okay. This compatible over here is a string which contains many different entries separated by commas, and each of those entries essentially tells you something about the type of device that you have over here, right. And ultimately, by putting together the fact that it's an ARM PL011, the system will be able to find out that I need to find a driver that can work with this ARM PL011 UART, right. Either that could be compiled into the system, into the kernel, or it could be a separate module which can be loaded at runtime, right. And this loadable modules is an interesting idea that exists in Linux. It basically says that a driver can be a piece of code, actually executable code, which will just directly be loaded into a particular location in memory only when required, right. So in other words, I don't need to compile all the drivers right into the system ahead of time. I can sort of go through my device tree, find out what kind of devices I actually have, and then load in those particular blocks of code, right, compiled code, into the appropriate locations in memory when required. So this compatible, this word over here essentially helps us to identify which drivers we need to load into memory. The reg entry over here tells us exactly about the starting address, and rather than giving the ending address, it gives you the size, the window size corresponding to this particular memory map that we have over here, right. And finally, the interrupts, we can just basically provide a number out here and say, okay, this is the interrupt which is connected to this particular device, right. So the point is, if I had written my code like this, it means that every time I change my device or if I build a new system, I need to recompile my kernel, right. Whereas over here what it says is I can have one kernel, and by just changing the device tree block, right, I can basically load different drivers corresponding to the system. So this is sort of a more general and hopefully a more flexible approach. And the idea is that we can basically reuse the same binary. What do I mean by binary? The compiled kernel image as well as the .ko or the module files that we can create and load in at runtime.